Welcome, focused learners, to the ultimate masterclass on cracking the Cambridge Computer Science exams. I'm so glad you're here. Today, we're taking a completely different approach. We are taking a hacker's approach to one of the absolute trickiest, most notoriously misunderstood topics in the entire syllabus: analog versus digital data in sound representation. Listen, whether you're sitting for syllabus code 0417, 0478, 0983, 0984, 2210, or the incredibly rigorous 9618 AS and A-level exams, this explainer right here, this is your backdoor into the examiner's mindset. Picture the exam hall. The clock is ticking down, the tension is high. Every single year, we see two very specific types of students sitting in that hall. First, there's Alex. Alex is the overloader. Alex writes furiously, absolutely packing their answers with raw computer science facts. They're listing sample rates perfectly, they've got the big depths down, they're dropping frequencies left and right. But you know what? They include zero actual analysis. Their answer is just a massive data dump. Because of that, they score a tiny fraction of the marks. Then, on the other side of the room, there's Sam. Sam panics. Sam rushes the paper, completely misses the specific command word requirements at the start of the prompt, and just writes this incredibly generic, vague paragraph that gets absolutely 0 points. Today, we are going to fix both of those deeply flawed approaches. We are going to find the backdoor into every single question you might face so you can start working smarter, not harder. Let's get into it.
Okay, let's dive into this roadmap. We've got a tightly structured agenda today, moving quickly from the core analog-digital dilemma and the top examiner warnings all the way through to building your procedural framework and wrapping up with a final cheat sheet.
Section 1. The Analog-Digital Dilemma.
So, what is the core conflict here? Why does this specific topic trip up so many incredibly capable students? Well, it's because the academic benchmarks for sound representation require highly logical, incredibly structured reasoning. The assessment framework heavily prioritizes analytical depth over superficial breadth. Think about it this way. When a question asks you to evaluate the conversion of an analog sound wave to a digital file, the examiner doesn't just want a simple dictionary definition of a DAC, a digital to analog converter. Anyone can memorize what an acronym stands for. No, they want to see the complete theoretical architecture in your mind. They want precise definitions. They want causal relationships. They want a clear, demonstrated understanding of the real-world implications of things like sampling rate and resolution. This is exactly where students like Alex and Sam completely fall apart. They provide a wide breadth of trivia, but absolutely zero depth. Look at this exact quote, drawn straight from the principal examiner reports. This is literally what they wrote. Analog versus digital data in sound representation is one of the most misunderstood areas in computer science. Let's fix that right now. This isn't just me trying to scare you. This is the very person holding the red pen, grading your paper, explicitly confirming that candidates struggle massively here. The Cambridge syllabus explicitly emphasizes that top-performing students exhibit connected, conceptual understanding. They want to see that you can transfer your knowledge to completely unfamiliar contexts. If you're just at home memorizing flashcards about sound waves, you're missing the underlying mechanics that actually score the big points.
So ask yourself this: why exactly do students find multi-step calculations and method marks so difficult? It's because calculating the file size of a digital sound clip isn't just a math problem. It really isn't. It's a test of algorithmic thinking. It requires identifying the given information in the prompt, breaking it down into highly logical steps, and systematically executing a solution from start to finish. If you just jump to the end, you lose. And hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2. Top 3 examiner warnings.
Now, what's really interesting about this slide is that we are going to take you directly behind the examiner's curtain to see exactly where those precious, hard-earned marks are just bleeding away. By understanding where thousands of students have failed before you, you can intentionally engineer your responses to avoid these exact traps. It's actually wild, because despite all the vastly different questions asked across the years, examiners consistently highlight the exact same trio of fatal errors over and over again. 3 major roadblocks stand between an average passing grade and a top-tier elite result when discussing analog to digital conversion. Let's break them down.
Here they are. Warning 1. Answers are far too vague. Listen, stating something like digital sound is better or a higher sample rate means better quality will earn you absolutely nothing. It's too generic. Examiners want specific technical details. They want you to explain exactly how the amplitude of the continuous analog wave is measured at set intervals. You need the technical vocabulary. Warning 2. Students constantly forget to check boundary conditions and edge cases during their algorithmic problem solving. When you're calculating file sizes, what happens if the file exceeds the storage capacity mentioned in the prompt? You have to consider the limits. And warning 3. Listen closely because this is the absolute biggest killer of them all. Answers completely ignore the specific context of the question. This is the classic mistake. Providing generic textbook answers that aren't specifically tied to the scenario in the prompt will result in an immediate cap on your marks. You could write a perfectly factual essay, but if it doesn't mention the specific scenario they gave you, you fail the question. Always link every single point to the given context.
And this brilliantly illustrates exactly what I'm talking about. Imagine seeing two answers side by side. On the left, we have Sam's generic answer. Sam wrote, "The sound wave is recorded into the computer to make it digital." Bam. 0 marks. Red pen everywhere. On the right, we see the absolute magic of the Peel framework. That stands for point, evidence, explanation, link. This is the ultimate computer science success blueprint. First, it states the technical point about the sampling rate. Then, it provides the evidence directly from the specific exam scenario. Let's say it's a 44.1 kilohertz recording specifically for a professional music studio. Next, it gives the explanation of how the continuous analog wave is quantized into discrete digital values. And finally, the link. It links all of that back to the studio's specific need for high-fidelity audio without distortion. The left is a student reciting a textbook from memory. The right is a hacker decoding the exam structure. That's how you turn red marks into green check marks.
Section 3. The Method Mark Strategy. All right, now that we know exactly what not to do, let's look at the ultimate solution. We are shifting our mindset from just avoiding mistakes to proactively hunting for marks. Enter the Method Mark Strategy. This is your safety net, and it's your point multiplier. It is an assessment framework where marks are awarded for demonstrating the correct logical process and completely clear working, rather than just arriving at the final answer. Let me give you a scenario. Cambridge examiners desperately want to reward logical, structured reasoning. If a question asks you to calculate the storage requirements for a 3-minute digital audio file, and you just do the math in your head and write down 31.7 megabytes, you might get 1 single mark if you're lucky. But if you show the calculation, if you explicitly write out the duration in seconds, which is 180, multiplied by the sample rate, multiplied by the bit depth, multiplied by the number of channels, you secure all the method marks. Even if your final arithmetic at the very end is slightly off because you are rushing, you still get the bulk of the points. Show you're working every single time. Now, to reliably secure those method marks under pressure, you must adopt algorithmic thinking. This isn't just a buzzword. This is the systematic process of step-by-step decomposition, appropriate data structure selection, efficient code implementation, and rigorous testing. When you look at an analog sound wave on an exam paper, I don't want you to just see a squiggly curve. Decompose it. I want you to see the continuous time on the x-axis, I want you to see the continuous amplitude on the y-axis, and I want you to immediately recognize the exact logical steps a computer processor must take to convert that continuous, infinite data into discrete, finite binary values. This mindset is the absolute secret engine behind successfully tackling completely unfamiliar contexts on exam day. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Section 4. Procedural Exam Framework. Let's move into the practical application phase. How do you literally tackle the exam paper when you are sitting at that desk, the clock is ticking, and the pressure is on? You need a systematic, standardized sequence. We're going to do a quick interactive workshop right now to prove this. Imagine Challenge 1, a data scan. Picture a highly complex computer science data table flashing in front of you with different bit depths and sample rates. You have a 60-second visual countdown timer to extract the core trend. Go. It's stressful, right? Now imagine Challenge 2, finding the flaw. You're looking at a sample paragraph and you have to spot the exact sentence losing marks. And finally, Challenge 3, speed writing. You have 30 seconds to write one perfect PEL paragraph. To survive these challenges and guarantee success in time-pressure scenarios, you must follow this 5-step procedural exam framework. Step 1. Deconstruct the question. Decode the command words immediately. Does it say identify, describe, or evaluate? They mean very different things. Step 2. Extract the relevant data from the scenario. Step 3. Select your analytical framework, like the PEL structure we just practiced. Step 4. Execute the analysis with absolutely clear working and clear notation. Step 5. Present it all with the correct technical terminology. So the crucial point is that this specific sequence guarantees systematic processing. If you skip extracting the data and just jump straight to executing, you end up exactly like Sam, missing the context entirely, panicking, and losing all the marks. Stick to the framework.
Section 5. Mastering Comparative Analysis.
Let's move to and see how this builds into the absolute highest level of the exam. We are now entering the territory of higher-order assessment objectives. This right here is how you unlock the top-tier grades in 9618 and across all the Cambridge syllabus codes. The syllabus demands that you can evaluate alternatives, compare approaches, and make justified recommendations. Listen to me. It is never, ever enough to just describe an analog signal in one paragraph and then separately describe a digital signal in the next paragraph. That's not a comparison. You have to put them in the ring together. To build a perfect comparative analysis, we can't just list facts. True analysis requires identifying similarities and differences. And more importantly, you must use comparative connectives, words like whereas, conversely, or in contrast. You must support each comparison with evidence from the provided scenario and draw conclusions about their relative importance. For example, if you're comparing a high sample rate to a low sample rate, don't just say one is bigger. Say something like, a 48 kHz sample rate captures significantly more high-frequency detail than an 8 kHz rate, whereas the 8 kHz rate drastically reduces the overall file size, making it far more appropriate for the simple voiceover application required in this specific scenario. Do you see the difference? That is how you synthesize information to score maximum points.
And I want to give you a massive top-tier examiner insight right here. The theoretical architecture of this subject rests heavily on integration with other syllabus areas. The principal grading reports specifically highlight that candidates referencing cross-topic connections achieve significantly higher marks. Do not trap sound representation in a little box in your mind. Connect analog and digital conversion to networking. Ask yourself, how does a much larger, high-resolution digital sound file impact network bandwidth and data transmission speeds? Connect it to hardware. How does the actual conversion process utilize the CPU, the ALU, and the memory registers? Showing this deeply connected conceptual understanding across different chapters is the ultimate hacker strategy. It tells the examiner that you truly understand computer science, not just one isolated chapter.
Section 6. The final cheat sheet. All right, we have deconstructed the exam, we've decoded the examiner's mindset, and we've built a bulletproof procedural framework. Let's bring it all together. Here is your final mental checklist. I want you to run through this for every single sound representation question you ever face. First, specific contextual links. Never write a generic answer. Always tie your technical knowledge back to the scenario in the prompt. Second, check your boundary conditions and edge cases whenever you are doing any algorithmic problem solving or file size calculations. Third, employ structured reasoning and clear working. Remember the method mark strategy. Show every single step of your mathematical or logical process to secure those points. And fourth, when you are asked to evaluate, you must identify similarities and differences, deliberately using comparative connectives to weave your facts together into one cohesive, undeniably strong argument. I want to leave you with a provocative thought as you approach your final revision. Look at your study habits right now and ask yourself honestly, are you just memorizing facts like Alex, sweating over textbook definitions, or are you executing a logical framework? The final system is simple. 3 rules that guarantee top marks. 1. Command word decoding. 2. Peel framework application. And 3. A strict time management matrix. The examiners have told us exactly what they want to see. They want analytical depth, step-by-step decomposition, and rigorous evaluation. It's time to stop studying harder and start studying smarter. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the absolutely biggest challenge you're currently facing. Our team responds to every single comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.